Welcome. This presentation explores the various degradation threats to diesel and drainage systems. Understanding internal and external corrosion risks, focusing on corrosion mechanisms and their impact on reliability and safety. This diagram refers to Corrosion Threats Handbook, Upstream Oil and Gas Production Plant by Energy Institute. System Overview. These systems are interconnected and critical for operations. Understanding their layout helps identify where degradation threats are most likely to occur. Here are the diesel and drainage system components. The first is diesel system, includes bulk storage tanks, setting tanks, service tanks, filtration and water coalescence units, power generation units and diesel consuming equipment. The second is drainage systems. Closed drain systems such as CD flash drum for separation, hazardous open drain system, OH drains tank for separation or water disposal, and safe open drain system or safe open drains tank for water disposal. Internal degradation threats. Internal threats are often hidden and develop over time. Regular inspection and fluid quality control are essential. Internal threats to system integrity includes, number 1 is, oxygen corrosion or O2, occurs when oxygen reacts with metal surfaces in the presence of moisture, common in diesel tanks and pipelines with poor sealing. Number 2 is, microbially influenced corrosion or MIC, caused by bacteria, especially sulfate-reducing bacteria. Leads to pitting and localized corrosion in stagnant diesel. Number 3 is, weld corrosion, happens at weld joints due to metallurgical differences or poor welding practices, can lead to cracking and leaks. And number 4 is, crevice corrosion, develops in narrow gaps or joints where fluid stagnates, difficult to detect and often severe. External degradation threats. External threats are influenced by environmental and mechanical factors. Protective coatings and insulation maintenance are key defenses. External threats to system integrity includes, number 1 is, external corrosion, caused by environmental exposure or humidity, rain and salt, affects outer surfaces of tanks and pipelines. Number 2 is, corrosion under insulation or CUI, moisture trapped under insulation leads to aggressive corrosion. Difficult to detect until significant damage occurs. Number 3 is, fatigue and fretting or FF, mechanical wear due to vibration and cyclic loading, common in pump connections and generator mounts. Corrosion types and abbreviations. Each corrosion type has unique causes and effects. Identifying them early helps prevent costly failures. Common corrosion mechanisms may occur in the diesel and drainage systems, includes, number 1 is, chemical corrosion, CO2 corrosion, carbonic acid formation in moist environments, H2S corrosion, sulfide attack, especially in sour diesel, acid corrosion, from acidic contaminants or cleaning agents. Number 2 is, localized corrosion, galvanic corrosion, between dissimilar metals, grooving corrosion, along weld seams or flow paths. Crevice corrosion, in joints and flanges. Number 3 is, structural and mechanical threats, SCC, stress corrosion cracking stress corrosive environment, erosion erosive wear, high velocity fluid impact, LME, liquid metal embrittlement metal weakening by liquid metals, FF, surface damage from repeated contact. Diesel system vulnerabilities. Diesel systems are vulnerable at multiple points. Maintenance and monitoring are crucial to ensure fuel quality and system integrity. Diesel system degradation points includes, number 1 is, bulk storage tanks, susceptible to mic and O2 corrosion due to stagnant fuel and poor sealing. Number 2 is, filtration units, high flow rates cause erosion and wear, filters may trap corrosive particles. Number 3 is, power generation units, exposed to vibration-induced fatigue and weld corrosion, heat and pressure accelerate degradation. Drainage system vulnerabilities. Drainage systems handle diverse fluids, making them prone to both internal and external threats. Proper design and flow management help reduce risks. Drainage system degradation points includes, number 1 is, closed drains, risk of internal corrosion due to trapped fluids and gases, flash drums may concentrate corrosive agents. Number 2 is, hazardous open drains, exposed to external corrosion and environmental contaminants, separation units may suffer from erosion. Number 3 is, safe open drains, subject to acid corrosion from chemical disposal, erosion from continuous water flow. Mitigation strategies. Mitigation is a multi-layered approach. Combining monitoring, materials, and design helps extend system life and reduce failures. Preventing and managing degradation strategies for diesel and drainage systems includes, number 1 is, inspection monitoring, use of ultrasonic testing, visual inspection, and corrosion probes. Number 2 is, material selection, stainless steel, coated carbon steel, and corrosion-resistant alloys. Number 3 is, protective measures, coatings, cathodic protection, and insulation maintenance. Number 4 is, design improvements, avoiding crevices, improving drainage flow, and reducing stagnation zones. Mitigation strategies and inspection methods for degradation threats. Degradation threat number 1, oxygen corrosion or O2. Mitigation strategies for oxygen corrosion may include, use oxygen scavengers, airtight sealing, and internal coatings. Inspection methods for oxygen corrosion may include, visual inspection, ultrasonic testing, and oxygen level analysis. Degradation threat number 2, microbially influenced corrosion or MIC. Mitigation strategies for microbially influenced corrosion or MIC may include, biocide treatment, avoid stagnant fuel, and MIC-resistant materials. Inspection methods for microbially influenced corrosion or MIC may include, microbial sampling, pitting detection, and fuel quality analysis. Degradation threat number 3, weld corrosion. Mitigation strategies for weld corrosion may include, proper welding techniques, post-weld treatment, and protective coatings. Inspection methods for weld corrosion may include, dye penetrant testing, radiographic testing, and magnetic particle inspection. Degradation threat number 4, crevice corrosion. Mitigation strategies for crevice corrosion may include, eliminate crevices, use sealants, and protective coatings. Inspection methods for crevice corrosion may include, borescope inspection, ultrasonic testing, and electrochemical testing. Degradation threat number 5, external corrosion. Mitigation strategies for external corrosion may include, external coatings, cathodic protection, and weather shielding. Inspection methods for external corrosion may include, visual inspection, coating thickness check, and soil resistivity surveys. Degradation threat number 6, corrosion under insulation or CUI. Mitigation strategies for corrosion under insulation or CUI may include, water-resistant insulation, seal insulation joints, and periodic inspection. Inspection methods for corrosion under insulation or CUI may include, infrared thermography, ultrasonic testing, and moisture probes. Degradation threat number 7, fatigue and fretting or F&F. Mitigation strategies for fatigue and fretting or F&F may include, vibration dampeners, flexible supports, and tightened connections. Inspection methods for fatigue and fretting or F&F may include, vibration analysis, dye penetrant testing, and surface wear measurement. Degradation threat number 8, carbon dioxide corrosion or CO2. Mitigation strategies for carbon dioxide corrosion or CO2 may include, corrosion inhibitors, control CO2 levels, and resistant materials. Inspection methods for carbon dioxide corrosion or CO2 may include, pH monitoring, corrosion probes, and thickness measurements. Degradation threat number 9, hydrogen sulfide corrosion or H2S. Mitigation strategies for hydrogen sulfide corrosion or H2S may include, H2S scavengers, ventilation, and resistant alloys. Inspection methods for hydrogen sulfide corrosion or H2S may include, gas detection sensors, SSC testing, and metallurgical analysis. Degradation threat number 10, galvanic corrosion. Mitigation strategies for galvanic corrosion may include, avoid dissimilar metals, insulating gaskets, and sacrificial anodes. Inspection methods for galvanic corrosion may include, visual inspection, potential difference measurement, and impedance spectroscopy. Degradation threat number 11, grooving corrosion. Mitigation strategies for grooving corrosion may include, improved flow design, erosion-resistant materials, and internal linings. Inspection methods for grooving corrosion may include, ultrasonic profiling, internal camera inspection, and flow monitoring. Degradation threat number 12, stress corrosion cracking or SCC. Mitigation strategies for stress corrosion cracking or SCC may include, reduce stress, avoid corrosive environments, and SCC-resistant alloys. Inspection methods for stress corrosion cracking or SCC may include acoustic emission testing, crack detection, and failure analysis. Degradation threat number 13, erosion. Mitigation strategies for erosion may include reduce fluid velocity, use resistant materials, and flow diffusers. Inspection methods for erosion may include wall thickness monitoring, flow analysis, and visual inspection. Degradation threat number 14, erosive wear. Mitigation strategies for erosive wear may include hard-facing materials, optimize flow paths, and remove abrasives. Inspection methods for erosive wear may include surface roughness measurement, wear particle analysis, and ultrasonic testing. Degradation threat number 15, liquid metal embrittlement or LME. Mitigation strategies for liquid metal embrittlement or LME may include avoid contact with embrittling metals, protective barriers, and resistant materials. Inspection methods for liquid metal embrittlement or LME may include metallurgical analysis, fractography, and hardness testing. Degradation threat number 16, acid corrosion. Mitigation strategies for acid corrosion may include neutralize acids, acid-resistant materials, and chemical-resistant coatings. Inspection methods for acid corrosion may include pH monitoring, visual inspection, and corrosion rate probes. Example case. These examples highlight the real consequences of ignoring degradation threats. Prevention is always more cost-effective than repair. Real-world impact of corrosion. Number 1, diesel tank failure, MIC led to pitting and leakage. Resulted in fuel contamination and operational downtime. And number 2, drain blockage, crevice corrosion caused narrowing and blockage. Overflow led to environmental and safety issues. Conclusion: internal and external threats are diverse and interconnected. Regular maintenance and smart design are essential. Top 10 frequently asked questions in terms of degradation threats to diesel and drainage systems. Question number 1. What are the most common degradation threats in diesel systems? The answer is, the most frequent threats include oxygen corrosion, microbially influenced corrosion or MIC, erosion, and weld corrosion. These arise from fuel contamination, poor sealing, and mechanical wear. Question number 2. How does microbially influenced corrosion or MIC occur in diesel tanks? The answer is, MIC is caused by bacteria such as sulfate-reducing bacteria thriving in water-contaminated diesel. These microbes produce acids and sulfides that lead to pitting and localized corrosion. Question number 3. What is corrosion under insulation or CUI, and why is it dangerous? The answer is, CUI happens when moisture gets trapped under insulation, leading to hidden corrosion. It's dangerous because it's hard to detect and can cause severe wall thinning before signs appear. Question number 4. How can I detect early signs of crevice corrosion in drainage systems? The answer is, use borescope inspections, ultrasonic testing, and electrochemical sensors to monitor joints, flanges, and tight spaces where fluid stagnation may occur. Question number 5. What materials are best for resisting acid corrosion in drainage systems? The answer is, materials like PTFE, Hastelloy, and glass-lined steel are highly resistant to acid attack. These are ideal for safe open drains handling chemical waste. Question number 6. How do I prevent galvanic corrosion between connected metals? The answer is, avoid pairing dissimilar metals, use insulating gaskets, and apply sacrificial anodes to redirect corrosion away from critical components. Question number 7. What inspection methods are recommended for weld corrosion? The answer is, use dye penetrant testing or DPT for surface cracks, radiographic testing or RT for internal flaws, and magnetic particle inspection or MPI for ferromagnetic materials. Question number 8. What causes erosive wear in filtration units and how can it be mitigated? The answer is, high-velocity fluid and abrasive particles cause erosive wear. Mitigation includes using hard-facing materials, optimizing flow paths, and regular cleaning. Question number 9. How often should diesel and drainage systems be inspected for degradation? The answer is, quarterly inspections are recommended for high-risk areas, with annual comprehensive assessments including ultrasonic testing, microbial sampling, and visual checks. Question number 10. What are the consequences of ignoring degradation threats? The answer is, ignoring threats can lead to fuel contamination, system failure, environmental spills, and costly downtime. Proactive maintenance is essential for safety and reliability. Thank you.